Hi everyone. Welcome back to the Edge AI 1 class. Let me first, before starting the class, please make sure you download the newest version of this lecture 4, in which I've added many, sorry, in which, in which I've added new things about the 3D plots and some new examples. Okay, so in the last lecture, let me see. In the last lecture, I believe we finished here, right? Let me just have a look. Okay, I'm open the Jupyter notebook. By the way, just to let you know that if you really use Anaconda Jupyter notebook a lot, to be honest, I would suggest you to install the traditional version, traditional Anaconda navigator, because through my usage of the cloud, this is actually a cloud. You can see it's a cloud environment of Jupyter Notebook. The good thing is it's extremely simple that you don't need to install anything as long as you have internet. You can run all whatever those kind of codes in the Anaconda server. The bad thing, however, is that I nowadays, all of these that they just want to earn the money, and you can see here, and myself has experienced many times of the CPU usage, the cloud usage is not enough, disk usage is enough because I typically just put some simple, a small data there. If you want to run some big projects, no matter you need to run, let's say, because some data itself, it can be many gigabytes. Here, the limit of everything is only 5 gigabytes. So here I use the, for example, you can see 21%, mainly it's the Python. I suggest, try to ask you to click this upgrade so they can earn money. You see what I mean? And here you can see environment, mostly it's just a Python. So, and also the CPU usage. This is the thing I hate the most, to be honest. Uh, let me see, Anaconda Navigator. You can just search Anaconda Navigator, click, and then you can download. So in this way, you're gonna, download the Navigator to your local computer or laptop, and then there's no those kind of time disk limit. As long as your laptop, the capacity CPU is enough, or if you have the GPU, so you can load import Conda. So that is the thing. But for this course, or for your homework, I assume this CPU usage it should be enough. Okay. Let's see. First of all, again, let me open those line things. Let me make it a bit bigger. Increase. Okay. Let's see where we stopped. We Yes, it's here. So last time we mentioned the matplotlib.pyplot.scatter, the scatter method. We in which, let me open this one. In which, you can see here I have an S parameter and a C parameter indicating for sizes and the colors, and I can control the transparency level alpha. So we can make, let's say I have how many 100 points here. We can see the sizes and the colors of these points are all different. By comparison, if you just use the plot, what's going all those points must be the same. It's, of course, you say, hey, I just want to, let's say I want to run it for, let's say, 100 times in the for loop. Can I? Of course you can, but it's just not that convenient. So that's the point. Okay, today we'll see something called subplots here. So why do we need a subplots? So where is why do we need a subplot? One thing is that by a subplot, sometimes, let's say in one cell of notebook, Jupyter notebook, I want to see this. I don't have to, let's say, run it in 4 cells, which is not that convenient. I just want to have a like a general view of all those plots. So I can have the subplot. And in Jupyter notebook, I should say in Python, not Jupyter notebook. It's pretty simple. Let me still let me see here. What I loaded. I just loaded MP and the matplotlib, right? Because I just reopen it. Either better just import. Let's if I directly make it, I guess it will be wrong. I can try and see. I have a linear space of this. Okay, equal to MP dot. Namespace. I guess it will be error, show an error because I have turned off the what the kernel of the Jupyter notebook. Let me just try to run it. It should show me error. Yes, it shows MP is not defined. In other words, I do need to import numpy as MP and import matplot lit.pyplot as plt. Okay, now if I run it, you see there's no error anymore. So x2 equal to mp dot linear space 0 oh, okay, I'd better over my cheating mode, otherwise I cannot remember those parameters actually. Okay, negative 10. Oops. Negative 10, 41. Okay, now what I can do is I will create a figure with axis. Figure axis equals to, let's say, plt dot subplot 2. Why? Because I want to just put it back. Why? Because I want to have 2 by 2 subplots, and hence I make it to be 2. And later we will in this class we will mention something about 3D plots. It's basically the same. The only the only difference is that we need to use add subplot this method instead of here. We can directly where we're here. Instead of here, we can directly, use dot subplots like this. But by the way, I'd better use AXS, make my life easier. Okay. I know here I use AX. Yes, okay. This is just a name, it doesn't matter. You can call it like this. It really doesn't matter. The thing is, I just worry later all my notations will be wrong. Okay, so here, after creating this 2 by 2 subplot, so this is to tell Python, hey, I'm gonna create a 2 by 2 subplot instead of just a plot. So now my objective would be axis instead of PLT, okay? Dot plot, and then I'm gonna have NP dot, here I have a cosine x1, and then I have a NP dot sine x1. Why? Because here I want to create what? I want to create a circle. And hence, everybody knows the circle parametric equation. Let me just okay, so if I have an xy coordinate here, so any point here, what is the coordinate? Okay, red color, it doesn't matter. Let's say suppose for any whatever point here, right? What is the coordinate here? It's gonna be what? It's gonna be code. Oh my goodness. Whatever. It's very difficult to write. Okay, give me a second. Let me see how can I type in Zoom. There should be a method for me to, yeah, it's gonna be cosine, let's say x and the sine. Let me call the theta, let's call t, and the c and the sine here, right? And that is the coordinate, assuming that the angle is t, okay? So this is the coordinate of this point. And that's why we have cosine x1 and the sine x1. Here we are using x1 to generate, those, point, and hence we have a circle. That's the reason. Okay. So now I have what? Cosine x1, sine x1, and then I can just, because this is to let the to plot it. And then I can have x0 axis 0 dot set title. Be careful, it's not a dot title because remember plot something dot title, right? No, it's set title, not dot title. You can try. Actually, I'm curious. Let's say circle. Be very careful here. You will later see that the axis display, the display will not be correct. And let me just make it plt.show. Let me just make it. Okay, so first of all, you can see text object is not callable. The reason is because of this tab title, because we should make it a dot set title. That's correct. And you can see here, the reason I name it to be axis display not equal is because you can clearly see from both the x axis and the y axis, the range is both of them are between -1 to +1. However, you can clearly see this one is longer. The x-axis, the scale is actually smaller than the y-axis, and hence looks like the x-axis is longer than the y-axis. But this is not what I want. I want to make it a real circle instead of displaying like a ellipse. I want a circle. So if you really want to enable a circle, then you can force Python to actually make the axis equal. So here, first of all, I will just copy and paste, but I will make a change. Sorry, first of all, I need to change the coordinate. So I'd better write it here. So we have already set subplot to right? So here it will be the axis by default. By Python default will be 0, 1. Come on. Okay. Let me just let me directly use my mouse to plot. Please excuse me if it's not good enough. This is 0, 1. This is 1, 1, 1, 2. So sorry. Oh, wait, my fault. Give me 1 second. Let me rewrite. 0, 0, 0, 1, 1, 0, and 1, 1. I'm talking about the coordinate of each subplot. So here I have figure axis equal to plot dot subplot 2, 2. So say here I'm adding the subplot for this one, right? And this one in the whole subplot, the coordinate is 2, 0, 0. And hence I say axis 0, 0. So what if I want to add something to this subplot? Then I'm going to say axis 0, 1 and similar things. So 1, 0 and a 1, 1. This is a 1, 1, not 1, 0. Sorry. How to clear rubber? I need a rubber. Okay, here. 0 and 1, 1, 1, and 0, 1, 1, 0, 1, 1. So these are the coordinates. So what I'm gonna do here is I'm gonna add it first of all to change all these to be axis 0, 1 instead of 1, 0. Second is I need to have axis 0, 1 and dot axis equal. This is what to force the core XY axis under equal scale. So scale, sorry. So if now you run it and you can see scale, and you can see this is indeed a circle, and you can see the what. So before -1, +1 here in the x-axis, and but here you can see it's -1, +1. It's smaller. You see, the sizes are indeed the same. You know what? Actually, I can add a figure dot height layout. This is to make a layout looks better. Otherwise, you can see they're all together. Okay, so yeah, a bit further, it's something for the display. It's not really a big deal. Okay, so this is the second thing, but here is not display equal, no, not equal. Circle display equal. So this is the second one, and then for the third one, it is let me see. The third one in the slides, I actually plotted what a square function since I'm opening my cheating mode, so I can directly read the code. 0, 1. Okay, so it's gonna be dot plot x2 square plus 3 times x2 plus 1. So I'm talking about this. I'm talking about this. And the function is this. And the last function is a hard curve, which is I don't know which one did I use, but I remember here we have so many hard curves. Yeah, I believe I applied this one. That is the hard curve I applied. So wait a minute. So these are the things here, and then let me just plot it. Number 3. Let me just open my cheating mode again. So the number 3 will be Wait a minute, did I plot this one? Let me just run it just in case something's wrong. Okay, it's indeed ugly. And let me just remove this. Hope it's better. Yes, it's better. And now you understand why by default it doesn't have this, because sometimes if we enforce the XY axis under the same scale, it will make it indeed ugly actually. Okay, now let's have axis 1, 1 dot plot. So I can directly read the code, which is 16 times MP dot sine x1 cubic, and then 13 times MP dot cosine x1 minus 5 times MP dot cosine 2 times x1 minus 2 times MP dot cosine 3 times x1 minus MP dot cosine 4 times x1. So now I can set up the title axis dot 1, 1, the axis 1, 1 dot set title, and then let's say hard curve. Here we go. So now we have all, you can see that now we indeed have all these four things. So this makes it, way easier for us. This makes it way easier for us, to directly read the bigger picture instead of like, if for example I don't really have this subplot, what shall I do? If I want to see all of this, I have to like use four cells, right? Each cell to plot one figure, and it's just not that clear in terms of reading, and hence we want the subplot. Uh, any questions here for the subplot? No? Okay. Then in the next one, in the next slide, let me see here. Uh, Here in the previous example, what we just ran was for a tutu. You can see plt dot subplots tutu. Okay, now in this example, we're going to create a 1 by 2 subplot. And the very interesting thing is that if you create a 1 by 2, right, it's something, to be honest, I don't think someone who wrote this matplotlib.subplot, the package, did some. It's just my personal view, some convenience setting. Because if I was the author, I would set no matter how many dimensions, I will set it to be two, like a 2D array. What I mean is I want to make this one to be 0, 0, make this one to be 0, 1, as what we did in the previous case, which is 2 by 2. Remember 0, 0, 0, 1, 1, 0, 1, 1. Unfortunately, this is wrong. So just want to let everybody know this is wrong. So what is the correct method? It's just very interesting that for if you only have 1 by 2 or 2 by 1, in other words, if you only have one row or one column, those kind of subplots, then your coordinate of axis gonna be on a one dimension instead of here 2 dimensions. So that is the thing. Let me just make it. I can actually copy the paste. Let me see. Can I just copy the paste here? Uh, Say I have this and I don't need a really x2, and then I have figure it's just 1, 2. Okay, be careful here. You can no longer write it to be 0, 0. You should write to be 0. And then I can just remove these two plots since I only have one subplot. And then here axis becomes axis 1. That's it. There's no axis 0, 1. That's the very interesting thing. Be careful. Okay, that's it. And if you don't believe, simple, let me just add it. You will see error. I guarantee you. Error. See it? It's one dimension, but two are indexed, and which is code number 4. Number 4 is here, and that's the reason. But if you change it to be 0, it will be correct. Okay, so that's the thing. about the subplot in 2D plots, 2D subplots. Again, here 2D means the figure dimension is 2D. Okay, it doesn't mean the 2D like 2 by 2 or how many or 1 by 2 something. No, it doesn't mean this 2D. The next one would be an example, which is a linear regression and the plotting. Recall that in lecture three, remember what we did was just class lecture three. Oh, what happened? Uh, it doesn't let me open lecture three. That's interesting, huh? Okay, here we go. Remember in lecture three, we did all those linear regression fittings. I think I did only one example. Let me just open lecture three here. So we did this and we showed how to use Python to perform the linear regression. Actually use the scikit-learn library, right? Is there a way we can visualize it? If the axis, the attributes is lower than 3 in general, yes, we can do it. And here is an example. Here we need to use this data example 2d.csv. First of all, did I upload it here? No, I have not. So let me have a look at my code. Did I? What is the what? Yeah, it's directed. There's no slash data slash, and hence I can direct it. Let me just put. I remember I will make a 3D as well very soon. So let me just put the 2D here. Okay. So now here I can do my fault. Sorry. I just realized this is under class 3 instead of class 4. Let me just redo it. Let me close it in case I make further mistakes. So here's the class 4. I still have the data, but here let me just let me just make my life easier in class. Class 4 is here. Okay, yes, I don't have this. So I'm gonna load it directly here. Instead of creating, a folder to save the data. All of these are on the server, okay, the Jupyter Notebook server. Okay, so now first of all, let me just open the 2D data. So it looks like this. We have a 1Y response and a 1D X1 attribute. And I believe 100 data, yes, 100. 100 data, and hence we can just, we can just fit it and then plot it. And I believe here, so first of all, to make the code self-oriented, I included those packages again. The truth is, that since you have already included those things, you probably only need to, let me see what I load. I probably only need to import the scikit-learn, that's it. But just to make it dependent, so I will still import all those packages. And I believe here first, we showed all 100 data, first observation to the trend of the data. After it, what we did was we showed the training data versus test data. The training data are those blue circles, and the test data are those yellow crosses. And then we also plot the prediction line. Okay, now let's see how can we make it here in Jupyter Notebook. So first of all, we're gonna import NumPy as MP, import pandas as PD, and then import sklearn from sklearn, import linear model. And then we need to import PLT, import matplotlib.pyplot as PLT. Okay, so now I'm gonna say what I'm gonna read the data. Remember the 5 steps we mentioned before in lecture 3, the 5 steps here. Loading data, getting the observation matrix and the corresponding response vector Y, splitting the data into 2 or 3 parts. 2 parts is the case that we don't need a validation data for tuning the hyperparameters. and then fitting the model using the training data, making predictions on the test data. Okay, so that's the thing. Now let's go back. First, we need to do what we need to load the data so that I have data equal to PD dot, let me see okay. I need to copy and paste, rename. No, it's 3D, but it doesn't matter. I can make it to be 2D. Okay, PD dot C read CSV dot CSV. Here I need to make it to be 2D. Okay, and now I can have x equal to data dot job columns equal to y. So I'm going to drop all the y columns and the x is equal to 1. That means I'm going to drop a column, then y equal to data y. Okay, so now let's do what I believe here I make a plot of the first observation of the trend of the data first. So I'm gonna, let's say, plot the data to observe the trend. PLT dot plot, and then I can say X, Y, BO, blue points, and then label equal to the observed data. And here I can make a plot X label, X, and the PLT dot Y label, Y, and then PLT dot title, first observation to all the data, then PLT dot show. Okay, here we go. So this is all the data that we have, and clearly it's a linear trend, right? It should be something like that. And hence, because I see this trend, and hence I decide to use the linear regression. Okay, now let's see how can we do the linear regression. In my slides, I code the other part here in another cell. So in my class, I will do the same thing. I'll use another cell. Again, since you've already loaded all those packages, you don't need to reload it again. So now I'm gonna do what? I'm gonna split the data for training, remember it? So I'm gonna have X train, X test, Y train. I can copy and paste, but I would rather write it again just to in case if you forget it, we can do it together. Y test equal to scikit-learn dot model selection dot model selection dot train test split. So I'm gonna have X, Y, and I have the test. If you forget, use shift in the table. It will show you, some a simple description. And you can see I do have, the keyword test size. Because once you have the test size, the train size is going to be determined automatically. So I have the test size equal to 0.3 as what we did before. So now after it, what should we do? We should fit model, right? So model equal to model, linear model, underline, linear model, dot linear regression. Okay. So now I will do what? I will fit model dot fit, use use the training data, X train, Y train, and then I will do what? I will calculate, excuse me, I will calculate the R2 score and then print it, and then print the intercept and the coefficients, and then now make the prediction. Okay. And now we'll have R2 equal to model dot score X train, Y train, and then I will have print uh, the R square coefficient is R2. I know I will make it like 4F for example. Did I use 4 or 3F? 4F. It doesn't matter. It just shows how many digits would you like to keep. And then I will print the intercept beta 0 as model dot intercept. Okay, now I can print co coefficient. That's a beta one. Yeah, I only have beta one, I believe. Do I have? Yes, I only have a beta one, so I don't have to use x dot shape something as coefficient. Okay, so now I have all this. What shall we do? We can just let me see. We'll predict for the test data, right? Which is number. Let me go back again here. We've already split the data, fit the model. Now we need to make predictions on the test data set. So okay, now I will make the prediction. Y predict equals to model dot predict using X test. And now I can have a for loop for I in range of how many Y predict I have, which is the length of Y predict. So for each record, for each data point, I'm gonna have, let's say, actual response is, I'm gonna use the ilog Y test, but ilog I, and then I can have versus the predicted, or I can write a VS predicted response. That's gonna be what? Simply just Y. Okay, so now I can just do it and what interesting. What is wrong? It didn't indent for me automatically. Oh, I know why. Because I forgot this. That's the reason why. Okay. Okay. Forgot one thing. Sorry. Forgot to set the what? np dot set big. Yeah. I want to set the print options like precision to be typically three because here you can see it's just really too long. I don't want to to show those np arrays the number of digits to be so long. So print options precision PICI equal to three, and hence you can why let me see here dot for okay let me put here. So now we have all these, and that's weird. This number should not be that long. Let me see here. Dot score precision dot rf. Yes, this is correct. And then the intersection is intercept. Did I make anything wrong? See here. Precision equal to three. Yes, precision equals to three. So that's true. It should have only three numbers, but why here I have one minute, 4F. Yeah, 4F should be the same things. Let me see why. Yeah, 4F should be like this way, and then I will have this is correct. This is also correct. The intercept of data. Okay, here's something weird. I already told it to set up the print options precision equal to three. But why it still shows so many see so many digits? I got pretty confused here. Looks like something here is wrong. That's interesting. I'm actually not sure. One method is this. Is to what is to restart the kernel. I'm just curious about this. However, by restarting kernel, I need to run this code because otherwise, here all of these are not defined. Let me just rerun it. So we have these, and then let me rerun this one as well. Still, there are so many digits that don't make sense because I've already set up the precisions to be three. So technically, it should include only three digits instead of so many digits. For example, it should be something like that instead of Okay. My fault. Okay. Yeah. Which is correct. Which should be in this way. Okay, here I go. But why? Wait a minute. Why this one still so what? Precision dot coefficients. Oh, sorry. Dot coefficient. No. I'm talking about this one. This one. Let me see. This should not be correct. But okay. Here we go. Sorry about this. Just to let you know, this is an array, but this is still a number, and hence I should use this. While this one controls all NP arrays, the precision of the NP arrays. Okay, good. We fixed this. So this is what we did before. With all this. However, here, what I want to do is I want to plot all these. What can we do? We can after running this, we can simply just let me say this one. Let's say now we will plot the training data, test data, and the predicted linear line. Okay, so now I can plot all these plt dot plot. First of all, let me just print the training data, X train, Y train, and then I will use blue O. And then I will say label equals to, let's say, training data. This is, we plot the training data, and now we can plot the test data, plt.plot, x test, y test. And now remember I use the y cross. Did I, did I use? Yes, I use y cross. And then label equal to test data. Okay, so now we need to plot what? We need to plot. First of all, let me just show you the result. PLT the show. Okay, first of all, let's see the result. So we have already got the training data and the test data. Now we need to plot the line, right? How do you how to get this line? Think about it in a 1D. Uh, let me see. Okay, I have this. So I have y equal to beta 0 plus beta 1 times x1, right? So this is my line. So in order to plot the whole line here, in order to plot the whole line, like, uh-oh, in order to plot the whole, okay, here we go. In order to plot the whole line here, we need to what? We need to get the beta 0 and the beta 1, which we've already had because beta 0 is nothing but a model dot coefficient, model dot intercept, and this is model dot coefficient. Okay, so now what we need to do is we need to use the linear space to generate, x coordinates, let's say for example from 1 to 10. For example, it's going to be 1, 0, from 0 to 10. It's going to be 0, 0 0.1, 0 0.2, whatever. You can use the linear space to easily get this. And then I will correspondingly calculate this y using this equation, right? Which is y equal to beta 0 plus beta 1 times x1. And then I will have both x array and a y array, and then I can use plt.plot to plot it. Get a point? So this is the idea of how can we plot this line here. So now we're gonna plot the predicted linear line or linear function, let's say. Okay, so to make it, I will have x equal to, let's say, np dot linear space, and then let me see, what did I use here? Where it is? Here. Actually, x max 200. Okay, x dot mean. So this is to find the minimum x number among all our training data. And then this is to find the maximum and the 200. In other words, I will generate a linear space between the min and the max. Why? Because I want to plot something, make sure that the line got across, the minimum x and the maximum x. That's the reason. And now I have x equal to this, and now I will have y equal to, let's say, I will use that equation. Remember, I will have model dot intercept which is beta 0 plus beta 1. What is beta 1? Coefficient, and then times x. This x is here. So that in this case, I can calculate the corresponding y. And now I can plot PLT dot plot x, y. And then I believe I use a red color. And then I can make label equal to, let's say, the predicted line. And here we go. Now I can just plot everything. Here we go. See it? I can add a line width actually. I believe, yes, in my slides, I add a line width. And then I also have a legend. I even forgot to show the legend. I forgot. Let me see here. Width line width equal to 3. And then label equal to this, and then legend. So it should show, yes. So let me rerun. Sorry, I didn't run it. Here we go. By the way, it's worth mentioning again that each time I run it, the corresponding numbers should be different. Why? Because again, we use this, okay? So every time it's random, it just, if you want to fix it, you don't want to see any randomness here, you can do, for example, X train and the Y train are the first, for example, let's say 70 data points. I mean, to just test an example, you can use it. However, in practice, never use it because this could cause serious bias of the training data, and it could cause inadequate model training or overfitting, Okay, so this is how we make this example in which we just use, apply the technique of plotting 2D figure, 2D plotting 2D functions, and apply it to the linear regression for for a 2D linear regression. Actually, I should say 1D because the 2D another dimension is from the response. I know it's not practical, but at least that shows an example how to make it automatically automatic generated by Python and applying the scikit-learn library. Okay, so the next one will be let me see. Okay. Here the similar example, but two things are added. Thing number one is let me see. Thing number one is I applied a subplot, as you can see. Thing number two is I write it into a class. I had a better write it because before I would like to say, hey, you guys just have a look at the slides, and I'm gonna skip to the next slide. I need to write it. Why? Because this is a class. I do want to show why do we need to write everything to a class, and second, we will later use it in another example. So I do need to code it. First of all, to answer the first question, why do we need to write it in the class? This is because later, let's say in classification, we will teach several different classifiers for example, like support vector machine, like KNN, like naive Bayes and simple regression, and then logistic regression, all this. And then if you use a class, it can make you can just define classifier and write a for loop inside, and it can make your things much easier. Second thing is, suppose here, let's say I'm a data engineer, and to handle different different data analytics to different data sets. So I can write a module. Remember how to write a Py module here, in which I define a class, and then for every time in future use of my data analytics, let's say for data set one, I need to do linear regression. Data set two, I need to do linear regression. Data set 1000, I need to do linear regression. I don't every time write it again. Instead, I just remember the class, I create an object for each data set as a object of, let's say, linear regression. And then I can just do it very, very easily. And that's the reason why we want to make it to class. Let me write it. I realize this is actually pretty important thing here. Let me just first of all, let me just comment. Actually, I guess I can copy and paste many things here. Let me just. It takes time because it's super easy to make mistakes here. Uh, you all see why. It's really super easy to make mistakes. Okay, so first of all, I'm gonna define those four things, right? So now I will have a class linear regression. Okay, so first of all, what shall we do? Define the initiate function, right? Define dot self. Here I want to put, let me see. Okay, first of all, is the path. I need to put, which is this one? I'd better have this in my main function. Here, let me just write a main. Okay, sorry. Let me write out the human language main function. And then I'm gonna have path equal to this. Okay, so now, so here's my initiation function. First of all, I need what? I need to define the data, which we did before. But here, in case we need to, cite to use data, I'm gonna make it to be self.data. I will copy and paste because I will use this self dot something a lot. And then it's gonna PD read of the path. Okay. So now I can do the similar things for the X and the Y's. Make sure the indentation is correct. Self.x equal to this, self.y equal to this. Okay. Uh, I believe I also have a text size. Yes, text size. Because for different data sets, if you want to apply, this creating objective and use the, linear regression class later, you may decide to have very different test size. And hence, I'd better make test size as an input instead of, to just define it. So here I will have self dot test size. I will again because maybe we will use these all those as attributes later, and hence I created as attribute. You don't have to. It's just to try to make things like easier for later. Okay, so these four things are in our initialization steps. And then I believe this one I can put it later in the plot because later I will have a plot function. Let me see here. I can temporarily do here. Okay, so now I can do this in my initiation as well because no matter what, you will have to train your model. And hence I will have, be careful that all of these gonna be what? It will be self dot instead of all these. Again, why? Because later we may want to see, hey, let's say, suppose, so in the main function, I'm going to do something like that. I will say, let's say, linear model 0 equals to the class linear regression class. And then I will make from the path, and then from test size equal to 0.3. And I will do this. So what if I want to say I need to have LR0 dot from data? You see what I mean? And hence I want to make it to be attribute. That's a thing. Okay. So where we are, okay, self dot train self y train self dot y train self dot y test equal to secular this, and then we need to change all of this to be 1 minute, 1 minute, wait 1 minute. Test size here, and you change it to be self dot test size. Here we go. Okay, so everything gonna be self dot y again because I want to make it to be attribute. Why do I need to make it attribute? Because in case later I want to cite them, I want to get them. Okay, so now after it, I can fit a model, right? I can, here's a training here. Again, I want to make a model to be self-model instead of model self. So linear model regression here. Here, I'm going to have self.train, self.y train here, and this sort of thing. R2, I should have the self because almost for sure I want to cite it before later because it's a coefficient. It's very important. Show how good or how bad the model will be. And again, here I can just copy the paste, not a big deal. Attribution, this one to be this, and then the R square attribute is here. Uh-oh, actually I have a mistake here again because I should have this self dot model. Wait, I'm define the model to be this so that it should have self dot model as well, self dot model coefficient here. And then I have y predict here. I can have, first of all, make the indentation and then self dot y predict, self dot a model. It will be self dot model, self dot x test. And then here it's going to be self dot, and then self dot here. Okay. So this is how we do the linear regression here. Let me see here. Let me just so I can use this to cite everything. Okay, so it should have okay. So now everything is cited here. Let's first run this class in case of any mistakes. So I should have path equal to this, and then sorry, I should add this one after it. Otherwise, I cannot read because path won't be defined. Okay, let me run it. Great, it doesn't have any mistakes. And indeed, you can see this is my initialization. So when I create an object called LR0, use this one, it's here. So I can do similar things. For example, I can have, let's say here's the path 2 equal to this. I can create another thing, which is path 3 equals to this, and I can create another one, or let's say 0, 0, let's say 0, 3 equal to linear regression, and then let's say path 3, sorry, here should be path 2. Here I can make it a path 3. Let's say I don't want 0, I want 0.1 to be path size, for example. Then I can just run this. And then you can see this is the result for the first one. This is the result for the second one. And you can see second one is shorter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why? Because I set up the test size to be 0.1. That's the thing. You see what I mean? It's super, super simple. If I define it in the class, I can just create a different, objectives. And then I can even say print LR03 dot, let's say R2. There we go, and it's this number. Here, of course, I didn't use f print limited the limited the what the float number digits, and you can see it is this value, but it's the same as this. The only difference because I use dot 4f where that is. Here I use a dot 4f so that it shows only four weirdness. It's here. That shows only 4 digits. So while here I didn't limit it so it's very long. So that's the thing. Okay. So this shows it's really really simple for us to if we create it in class. It makes your code much more robust. But to make my life easier, I can just one thing I do want to mention here is I don't even have to write this 0.3. Why? Because if you pay attention, sorry, I remember when I wrote it. Yeah, sorry. If you pay attention, when I define here, I can write it to be 0.3. This means if I do not have this test size parameter, it will by default set to be 0.3. So I can for example just run it and it will kind of see. Even if I didn't give, the test size, it's still correct. Nothing's wrong. Why? Because or let me just add this. Let's say I, yeah. So in this case, you can see the numbers, which is easier from 0 to 30, to 29. Hence, it has a 30. Or if I can write it, to be 0.1, then I have 10, 0 to 9. That's the reason. This is, just a method to make you a lazy person. That's the thing. You don't have to, but this is like for any function or class or something. That's a default definition. In case you're lazy, you don't want to set up again. So that's the thing. Okay, now we need to have a look at the plot part. Currently, we've just returned everything like for the pure linear regression itself in the class. I have not plotted anything, right? So to plot it, I want to define the function here. It's called, let's say, subplot function. Is it subplot? Yes, it's a subplot. So I will make it a subplot function. I will call it, let's say, subplots self as well, because assuming here I don't need to make any function-based parameters, and hence I can similar things have access equal to plt dot subplots 1 2. Why? Because it is 1 by 2. So let me just make sure it is okay. Okay. And now, first of all, remember what we did here? We plotted the original data first, and then we plot, a new, figure which includes training test data sets plus the prediction line, right? So similar things here for the subplot, the left plot here will be the original data point, and the right one will include everything. So here, please allow me to be lazy. So I'm gonna just directly copy and paste from what I did before. However, I need to be careful that I cannot use PLT anymore. Instead, I need to have axis, let's say 0 dot plot, and then I need to have, oops, self dot x. Otherwise, it will be wrong, and it will tell you, hey, what is x? You've never defined x. Self dot y, the observed data, and then several things, axis. I cannot say X label anymore, and I need to have X set X label. And to be honest, I personally very dislike this. So why don't you, the author of Matplotlib, why don't you create everything just constantly? So everything to be set label, a set X label or X dot X label. Instead, like in subplot, I need to write, hey, set X label, and in plot, I will write X label. It's just pretty confusing. And personally, I don't like it, but I'm not the author, so I have no choice. Here I have this, and then I will have similar things. Access 0 dot set title to be this, and then let's assume I can write plt dot show because just in case of any mistakes, I will have access 0 dot legend. Okay, so similar things. Let me just set these because I want to copy and paste these things again. Okay, so now I have this. Let me just have lr0 dot subplots. Let me run it in case of any mistakes. Okay, it looks good. I didn't have any mistakes here. So here's the left plot, and indeed I just I just plot everything here. Okay, now we need to consider the right plot. What is the right plot? It's nothing but here. Here, I don't need this one anymore. I can just, delete these comments. Okay. Okay, so again, I will have a new axis, axis one, and similar thing, self dot x train and then self dot y train, and then this is this, and then self dot x test, self dot y test, and change it to the axis one. And then here is the same, and self dot, self dot. Okay, here is something I want to say. Here, I assume that I will never ever use this x, x, and y, y. Why? Because it looks like they are just transient variables for me to plot it, right? And hence, I don't write it as, I don't define it like in the very beginning, like initialization function self dot x, x self dot y, y. No, I don't do it. Instead, I just directly write it like this way to show that, hey, these things are just transient variables. When you're running the code, it's needed. I mean, running, I should say, when you're creating a subject and after when you do the subclass function, I will need it, but I will never, ever need it anymore after it. So who cares what are they? So I don't define it to be self.xx. And hence I just directly write xx and yy here. And then I will have this, and I will have, let me see here, predicted line, and then legend one dot here, not axis one dot legend, and plt dot plot. Okay, plot. Okay, so now I should have everything. Oh, great. Oh, I love it. Which line? 15, line 15. Did I get a mistake on? Huh? Line 38. Sorry. Line 30. Okay, here. Okay, here we go. And you can see we correctly, plotted everything. This shows that I think the main reason, the main reason for me to spend time to write it down is because later we'll use it, and we just copy and paste, instead of rewrite everything again. So this is exercise 4.2. Let me just write a marker before it. Oh, above, not below. Sorry, and I can make it to marker. So you just press ESC and then you press M. So it will automatically be marker. Or if you see here, I press C and then I will. I don't. Whatever. Okay. Suppose it's code. Now you press escape and then press mark N. It will be marked automatically. So I will have it is a what exercise for two. Here we go. Okay, so now let's continue. Okay, so these are from the first slide till here, it is everything about the 2D plot. Again, I mean, there are so many libraries, very good Python plot libraries, and even for Matplotlib itself, this is actually a very small part, but the main part here. Since we don't have enough time, I believe all this is completely is actually more than enough than what we need in this class. So this is everything for the 2D plots. And now we're going to start introducing the 3D plots. Similar to 2D plots, we want to plot those kind of lines and points, and hence they are the very first examples. And let me just do it to make it consistent. I will still do this, but I choose that since you have already run it in practice, you don't have to. Here I don't need a scikit-learn anymore. I don't need even PD. I need a NumPy and a PLT. Okay, so now I will have, let me open it. I cannot remember the parameters. Okay, so now I will have, first of all, I will build a parametric equation. So in this specific example, we will plot helix. So for helix, the parametric mathematical equations are like this way. Xt here t is a parameter, okay? The parametric variable. So xt equals to cosine t, yt equals to sine t, zt equals to t, and this is the thing. And then we will need to use this our code inside to make it programmable. And first of all, we will build the parametric equations for a 3D helix. So I will have, let's say, z equals to, oh, wait a minute, in my here, I wrote a z line. The reason here in the slides, I wrote a z line instead of z is because x, y, z will be used here. But you can call it a z2, z2, x2, y2 versus x1, y1, z1, whatever you want, Here, let me just follow the slides. Z line equal to mp dot length space 0, 20, 1000, and then y x line equal to mp dot linear space 0. Sorry. Because here's a mistake. Because here I have xt equal to cosine t, y equal to sine t, and z equal to t. And hence, this z line is actually the t. So I should have xt equal x line equal to not linear space anymore since I've already created it so that I can directly write xt equal to sine t. Huh. I should have realized a mistake. You know what? Here my x line in my slides, my x line should be the y line because it don't matter. It's just just exchange of x and y coordinate. It's really not a big deal. So it's gonna be mp dot let me follow the slides sign or just let me follow the mathematics. X equal to cosine z line, and then y line equal to mp dot sine z line. Uh, Okay, so now I'm gonna plot the 3D helix line. So I'm gonna have x equal to plt dot figure dot add subplot. Unfortunately, Matplotlib again for the 3D print, you can see it's very very different from the 2D. It's more like 2D add a subplot, and the truth is yes, you're correct because for 3D again I don't know why. I mean the designer, the authors of the Matplotlib write it in this way, but looks like for 3D it's different. They don't allow you to use the same format as 2D. I remember many years ago, about 10 years, approximately 10 years ago, when Matplotlib just were just coded, they just published that I forgot what is the code, but I remember at that time we just learned it, and there was something similar like PLT dot plot, and there's a function called a PLT plot 3D plot I remember Plot 3D, but now in new versions they gradually like eliminate it, and then if you just search it, you will see in most of those kind of codes or something they use this. So to keep to make our life easier in future, so I continue using this format. The good point is that I hope it will not be eliminated. The bad point is that if you compare the 2D Matplotlib versus the 3D, you will see something's just very, very different. Anyway, then I can say projection equal to 3D to let it know that it's a 3D plot, and then AX dot plot, let's say X line, Y line, Z line, and then here I use yellow and label equal to helix helix line. So in this case, I can plot it. Let me say x dot legend and then ELT dot show. Okay, here we go. This is how you can make it. And in my slides, I also created some different points. Let me just add these. I'm gonna have plot 3D points. And then I have x equal to 0.0, 0.8, 1, 0.5, 0.3, negative 1.22, and y equal to 0, 0.5, 0.3, negative 0.2, negative 0.8, 1.4. And then I define z equal to any just randomly, create something and p dot random dot random 6. So this means I'm gonna randomly generate 6 z data. And now I'm gonna plot ax dot plot x, y, z ro label equal to 3D plots. And the similar things you're gonna set, the different labels dot set x label, set y label, y, and x dot set z label, z. Okay, so now here we go. So we have this helix plus those how many? 1, 2, 3, 4, 5, 6 points. Okay, so this is how we this is a very, very first example of the 3D plots. However, there's an issue. I don't know whether you've seen it. 3D is something different from 2D. Like 2D in this way is great, but 3D is, because our screen, our computer screen is 2D, it's a plane. I want to, for example, see from this direction, I want to see different directions. And hence, I wanted to kind of like allow me to rotate. Unfortunately, you can see here, it doesn't allow me to rotate by default. Actually, later we'll see it's just to save the server, the space and the usage of the server CPU. That's why it doesn't allow you on default. But if you really, really want to make it, what should you do? You can install a package called IPY-MPL. And this one actually will enable these kind of interactive features of Matplotlib. Let's do it. So first of all, remember, how do we install those things? We need a magic, operator here. I will have the magic operator percentage. It is PIP install IPY-MPL. Okay, run it. And then it will take some time to. Oh, it's so fast. I know why, because because when I prepare the class, I've already installed it and now I deinstall it, and that's why it's so fast. The truth is that if it's the first time you install it, it should take some time. You just wait a little bit, and then it will show you everything's finished. And then be careful of this. You may need to restart the kernel to use update packages, and which is absolutely correct. Yes, you do need. Again, kernel, start kernel. In some cases, you may even just refresh the whole web page to make sure that the restart is thoroughly, it's really thorough enough because I don't know why sometimes even if you just, maybe the response of the server is too slow or something, sometimes even if you click, uh, you click restart kernel, restart, sometimes it will still show you an error. So what we can do is here, I just copy and paste here, and then before you plot anything, I can simply just write matplot lib ipympl, which is the package that we just installed. Okay, now let's run it to see what's gonna happen. Okay, here we go. You see it? We have this. So these are windows for you to operate, and we can make it bigger. And then the best thing is I can just click it and here I just put my fingers on my mouse and I didn't I have not released it and I just drag it. So you can see I can indeed rotate it. Again, this feature in 2D it doesn't matter, but in 3D it does matter because our screen is 2D. So in order to check your 3D plots clearly, you'd better have these, features. And you can explore some other things. For example, you can just, make it change. Sorry, here's because the server is a bit slow. That's the thing. And then you can even move it. This is the move. You can just move to see the coordinates are changing. You can just move to different coordinates. And if you play it too far, you cannot find it anymore. You can just click this one to, to recover to the initial status. So this is to show how you make it here. And if you use, let's say, an IDE, let's say PyCharm, which is the most popular Python IDE, it will just open a new window so that everything's, those kind of interactive features, by default, you will see it. Or if you install the Anaconda Jupyter notebook locally by Navigator something, then you can write it to be you don't have to install anything, but you can just write percentage matplotlib. Here you're going to use Qt. Qt is actually a self, Python oriented, Python self-built package for making those kind of GUIs. So you can directly make it. Okay. So that is the thing for this slide. In the next one, we're gonna see the scatters. Very similar to the scatter versus plot. We can, compare the scatter versus plot. Sorry, very similar to the scatter versus plot in 2D. Here in 3D, similar things. I can again just here, just copy and paste. Actually, I even don't need. I can just do everything here. So instead of, let me see here, the plot here, I will all remain the same. But here, instead of using plot, I'm gonna use scatter. In my slide, I actually have defined, let me see, I've defined the color and the size. Okay. So here are some more things. I can change color equal to mp dot random dot rand int to generate random integers between 1 and 100, and then the size equal to 6. Why? Because I only have 6 data here. And then I can do the same thing for size equal to mp dot random dot rand int, and it's gonna be what? 5 to 200. 200 size equal to 6 as well, because I only want to generate 6 numbers. Okay, so now I have, let me see, did I generate a Z already? Yes, so let me move here. So I'm gonna have this one, and then instead of the RO, I will have C equal to color, and then S equal to size, and label is still the same. Again, if you forget, just cable plus shift plus cable, it will show you the documentation here, and you can see as C, and then I can just label these, and then legend and plot. Here we go. Okay, and indeed you can see they have different, sizes and colors. You can rent again, it will be all different. Why? Because we use random. So the sizes and the colors of these 6 points would be different. However, for the helix line, it's always the same. Okay, so this shows you the comparison between the scatter and the plot. Uh, Next, let's do a pretty interesting exercise, which is to plot this double, helix structure of our DNA. Uh, First of all, we've already plotted the helix so that we can generate helix at a one. We can get helix one. For helix two, what you can see is I have the same z, but x and the y axis they just exchange. Why? Because for the DNA, it's just a 90 degrees rotation, and hence it doesn't matter. Hence it means your y is my x, and your x is my y. It's like this. Okay, I'd better just already code it, I guess. This is gonna be where I'm at. Let me make a marker. Exercise 4.3. Okay. So now to make it self-oriented, let me just copy paste these. Let me have everything here. Hate to rewrite it again. So I have these, and then of these, let me see the parameters. Okay. 100. And then the reason I write this in this way is because I tune the parameters to make it not to be too big or too small, and hence you have 0.1, uh, and also z1 over 5. That's the reason. Let me just directly follow the what follow. Let me directly follow this y1 equal to this, and I here space here I have a parameter 0.1 to indicate the radius of it, and then this one is z1 divided by 5, and then similar thing, z1 divided by 5, and then 0.1 times this. Okay, so now I'm gonna have so this is helix one, and now we're gonna generate helix two, which is z2 equal to z1, and then x2 equal to y1, y2 equal to x1. It's just to rotate x and y. So now I'm gonna plot the DNA. So I have x equal to plt dot figure dot add subplots. Come on, it doesn't show. Anyway, I have to write. And then projection. Again, if you forget shift and table, it should show. Oh, looks it doesn't show the thing for dot add subplot. Anyway, projection equal to 3D. Okay, so now I'm gonna plot the first helix dot plt x1 y1 z1. The R label equals to let's say first helix, and then let me line width equal to 4. Okay, so now I can do the second thing, x2 y2 z2, and then label second helix. Okay, after this, this will show the main two DNA, and then I can just show it. Okay, and then that's really ugly. No worry, later we'll use X-lim and Y-lim to adjust, the reason because the scales of those axes. No worry, but at least I mean it looks not it looks something already. No worry, I'll add this. I remember point 0.5. Oh no, point 65. Okay, I will have x dot set x lim 3D. This is just to show the limit. This one ugly is because the limit of x and y are from -1 to +1. But I force it to be something else so that it's like we can stand at a further point, we see it, and it will be much better. X dot set y lim 3D, and then negative 0.65, 0.65. Okay, now let's run again. See it? It looks much better, and it does show something like what? Let me rotate it like a double helix chain. Okay, the double helix. But now we are missing some chains. As you can see in my slides, I do have those chains. How can I make chains? Don't forget that I have already generated the Z1, X1, Y1 arrays and also Z2, X2, Y2 arrays. And hence what we need to decide is, we have all those points. Every how many points you want to plot a chain. Here I believe, yes, here I plot a chain for every six generated points. So let's do it. Here I'm gonna, let's say, for I in range length of Z1. This is to know how long the total array is. And then if I percentage 6 equal to 0, this means, plot a chain for every, you know what, I can actually make it to be a parameter. Let's say C equal to 6. Then make it to be C for every C generated data point. And then I can have x dot plot, and then I have what? I have be very, very careful here. I need a double array. Why? Because this array is for me to put the coordinates, y coordinates, and the z coordinates. Be very careful here. I have plot. So here are for axis. I have x1i, x2i, and then x3i. And I will do the same thing for y and z. y1i, y2i, y3i. You can actually use what a scatter. Why do I need to write it this way? Why don't I use just one uh, 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 use one one-dimensional array? Because here we're using plot. Plot only allows one the what only allows here this to be x, this to be y, this to be z, and hence you cannot write all of these together. Why? Because I have an if statement. If I percentage c equal to 0, and that's a thing. And I believe here I'll write a line length. Yeah, line width. Sorry, line width equal to 1. Okay, so now I can make it. Let me just set X label, set Y label, and then set Z label so that when I rotate, I won't like get lost. Okay, so X3 is not, well, let me see. Oh, sorry, my fault. Yeah, here's something very confused, consuming. So totally it is a 3D, but for each x you have only two axes. Why? Because of this. Because you're gonna have one point to another point. There are 2 points here only. So let's see, one z, and then remove this z as well. Okay, here we go. So now indeed you can see it looks like a DNA chain. And here for every 6 points, I have a chain. Here I can make it smaller. Let's say c equal to 3 instead of 6. Sorry, c equal to 8, let's say. So every 8, indeed you can see these chains are no longer that dense. It's actually less dense. Or if I make it to be 10, it will be even smaller. It is. Okay, so this is how I make two helixes and all those kind of chains, which which is this exercise 4.3. Okay, and then after making those kind of points and lines in the 3D plot, we need to consider those kind of surface contour, those things. However, the fundamental of generating the data is actually in the 3D plot is actually MP.mesh grid. It's just similar to like a linear space. The mesh grid generates those kind of coordinate grids for 2D. And here we can see example. I have x equal to 1, 2, 3, y equal to 4, 5. Since this example is very, very simple, I'm not gonna run it here. We can directly see it. If I use x, y equal to np.mesh grid xy, You know the result? The result will be this. So XX will be a 2D array, which the first element is going to be 1D array, which is 1, 2, 3. The second one will be the same. While Y is going to be 4, 4, 4, and 5, 4, 5, also a 2D array. So what's the point for me to generate these things? Because via this way, we can generate X and Y, and hence we can generate a Z. And after it, we can, create an object in a 3D plot. So I believe I wrote here. Let's say if we want to plot a 2D function, which is y equals to 2x. Remember what we did? We first generated x use this np dot linear space. We have x, for example, equal to 1 to, let's say, 10, generate 1,000 points. And now I have y equals to 2 times x. So in this case, I generate, the function, and I just plot x and y. I can plot this function y equals to 2x. Remember, it's in lecture 2 or 3, maybe 2 probably. How about for 3D? Of course, you can write two fors to generate brutally, I mean by yourself. However, we can also use np.meshGrid. It's a method which is already created. So for example, if I want to generate a function which is z equal to x squared plus y squared, first of all, we need to generate a grid of x, y's, right? Then I'm going to write z equal to x squared plus y squared. But how to generate x, y's? And this is the method. If your x's are 1, 2, 3, y's are 4, 5, using mesh grid, it will make you something like a cross. Like for example here, I plotted x, x, and y, y. And you can see there are these 6 points. You see the point? It's nothing but just a grid here. Of course, you can make it even dense so that it will be what I mean this, you can make it even dense so that all here we sorry, it's pretty small, but you can make it pretty dense to make this grid throughout the whole uh the whole coordinate here. And that's why we name it to be mesh grid, because we want to make a mesh and generate the grid coordinate for 2D. And then I can use z equal to the function of x and y. Then I get the projected z, and hence I can create the whole thing. That's how we make it in 3D. Indeed, it's actually the same as NP the linear space. Okay, let's see some examples. The very first example is a 3D scatter plot, but it's like a sphere. I hope you still remember the parametric equations of a square, which is x equal to r. R is the radius of the sphere of cosine theta sine phi, so that we have two angle parameters. One is theta, one is phi. It is actually this meaning. Let me see. It's consider it is like a 3D, so that I can have a sorry, my plot is very bad. Let's say something like this. And now let me plot a wait a minute. Let me consider a point, let's say here. So this point has two angles. The first angle over here, which is, if you can I have a dash? No, it doesn't allow me to print a dash, but let me just make a line. So the first, let me just directly to save my time. Let me just write it. So this is something like the theta, and the second one will be like this, which is here. And then let me use another color, let's say yellow color, and then this is like phi. So it has two angles. Once I know the phi and the theta, I can express, of course, with the radius r, I can use this like a polar, coordinate. I can express a point in the 3D coordinate. Okay, so the parametric equations, this x equal to r cosine theta y phi sine phi, y equal to r sine theta sine phi, and z equal to r cosine phi. To make it easier, I just consider r equal to 1 in this code. Okay, let's code it. And then I'm gonna have theta equals to mp dot linear space 0, 2 pi, and 30. And the phi is the same. Okay, now I'm gonna use mesh grid to generate theta phi equal to np dot mesh grid, and then I'm gonna have theta phi. If you want, you can print theta and then print phi. It will be a lot of points indeed. And here we go. Is it? And then you must ask, so what is the meaning for those? The meaning is exactly here. Of course, here will be much denser than these 6 points. They can be maybe 600 points something. It is just every, among every coordinate, as I just mentioned, every different coordinate, and we'll have a point, point like this, all the points. It's very dense. And hence, correspondingly, I can compute the z. Okay, so let me go back to my code here. I have these, and now I can use this parametric equation to generate the z. So to generate x, y, and z, because here I only have theta and phi, assuming r, the radius equal to 1. So now I can have x equal to np dot cosine theta times np dot sine phi, and y equal to sine np dot sine theta times np dot sine phi, and z equal to cosine np dot cosine phi, and make sure it's correct. Yes, it's correct. Okay, now I can just plot x equal to plt dot figure dot add subplot, and then projection equal to 3D. And now I can have scatter x dot scatter x, y, and z. And now I can just set labels, those no things. I'm just copy and paste. PLT dot show. Here we go. Theta not defined. Wrong spell, wrong spell. Where am it? Number 5, theta's here. Okay, here we go. That is how you can plot it. Again, since I've already applied this mode, IPY and PL mode, so that all those figures will be interactive, and also I've imported these two packages. So here I didn't write anything before it. That's the reason why. And yeah, that's how we make it. Oh, here I still have a title, but anyway, I'm lazy to write it here. To save my time, we are gonna finish this scatter plot here. The next one will be a surface plot. For a surface plot, actually nothing changed. The only thing is here, plot surface. Let me just write here. Let me just move it to another cell, although I can actually do it here, no difference. So the only change is actually this line. Instead of dot scatter, you're gonna have dot plot surface XYZ. And I believe I add some alpha parameter. Yes, alpha parameters to set up the transparency level. And you can indeed press shift in a table, and you can see here. And why don't show the alpha? That's interesting. I I believe if you go to the Matplotlib, surface, the documentation shows alpha. But anyway, we just directly use alpha equal to 0.3, for example, and then we can see the result. This is 0.3. And you can see indeed it's pretty transparent. By comparison, if I make it to be 0.8, it will be very dark. See? It's much darker versus 0.1, almost transparent. Let me just change it back to 0.3. Okay, so this is the thing. I'd better add a title. Set title, because later I will just come and paste the code here. It will be from a sphere surface plot. sphere surface plot. Okay. So the next thing I want to introduce is the contour plot. Again, the only difference the only difference is this line. Instead of surface plot, you just make it to be contours 3D, and then this 30 is density level. Let me again copy and paste. And here, instead of plot surface, I'm gonna have a contour 3D, XYZ. We don't have an alpha anymore because it's not a surface plot, it's just contour lines. I'm gonna have, let's say 30. And you can compare it. Let's say I use 10, and you will see it's gonna be pretty sparse. And if I put 100 here, it will be like a surface. It's kind of like surface. You can of course just ignore it if you don't write it. Let me see. Arcs extendable, and let me see here. It doesn't show. I'm not sure actually what is the default. Default is like this way. Okay, okay. Ignore it. Let's still put 3D. Uh-oh. No, 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 no. Sorry, it's not here. Let me see, where should I? Here. Okay. So this is the surface plot. This is a 3D contour plot. And the next one is we are going to combine the contour and the surface plot. And we want to make those kind of, contour lines. Something different is that I want to use the ZDIR keyword together with the offset number. So I will push those contour lines onto my corresponding coordinate walls. Let's see how can we make it. So first of all, uh, to make it independent, I'm still gonna write all those. Now I'm gonna generate because here in my example, I created a paraboloid, and hence I'm gonna generate a linear space -1 to +1, 100. Okay, x squared plus y squared is equal to x squared plus y squared. So I have x equal to mp dot linear space -1, +1, 100, and y is the same. Y equal to mp dot linear space -1, +1, 100, and then xy. I need to create a mesh grid. You create mp dot mesh grid x and y. And now I can have v equal to create a uh, per, per, wait, how to read it? Paraboloid. I will make z equal to x squared plus y squared. Okay, now I can plot it. First of all, I will apply x equal to plt dot figure 3D. And now I will plot the surface, plot surface x, y, z, and I will create an alpha equal to, let's say, 0.5. Okay, so now we can just plot it, plt.show. Huh? What is wrong? Projection. Okay, here, make it, let's say 0. It's a bit too transparent. Okay, so in this way, I plotted up this surface. However, I want to plot the contour. So how can I make it like in this slide, the contour on those different XYZs? I need to use the offset. Okay, so let me have here x dot contour 3D XYZ. Okay, I'm gonna say ZDIR equal to X. So this means I'm gonna use offset here. I'm gonna push it into the X. Oh, wait a minute. I'd better wait a minute. I'd better do this. Otherwise, I will make it chaos. Set labels. Let me just have this. Then you will know which one is which. So this is the X. I wanna say create something. So this is part one. I want to have the contour towards X and push it on this square, on this plane, sorry. And how to describe this plane? Let me plot it. What I'm talking about to make it to be to this plane. How to mathematically show this plane? And then we can see this plane. What is the coordinate of wait a minute. My fault, my fault. Not this plane. I should say the other plane because it's offset is -1. I'm talking about this plane. And in this plane, indeed, I can see that this plane, the coordinate is x equal to -1. See it? And hence here, oops. And hence here, I'm gonna have quantum 3D. I'm gonna ZDR is x, meaning that hey, this is the direction you wanna push towards x, and offset equal to -1. And hence, I will have something from here. And similar things, I can do it for y and z. So if for the y coordinate, which is here, I want to plot it where? I want to plot it here, right? And hence, the offset is going to be +1 because I want to break everything here in which the coordinate is +1. And for the z, I want to plot everything here. And everything here, what is the coordinate? The coordinate here is z equal to 0. Here it doesn't show clearly, but this point, oops, the low, the lowest point should be z equal to 0. Why? Because z equal to x squared plus y squared. So the minimum of z clearly is 0, and hence offset is 0. And now let's see how can we show it again. Okay, what's so ugly? Let me see. Wait a minute. Did I make any mistakes here? Okay, by the way, first of all, we need to apply the C map, which is a color map. Second thing is that we better set up the X, Y, Z linked 3D to make it better. First of all, let me apply the X, Y, 3, the name. X dot set X linked 3D to be -1, +1, -1, 0, 2. Okay, -1, +1. X dot set y lim 3D to be -1, +1, and then x dot set z lim 3D to be 0, 2. Second, that's the reason why z. Okay, here we go. To make it as beautiful as showed in the class, we can add another import another thing here. Import mat. Oh no, from matplotlib import CM. This is just the color map package. So here I can say the CMap, and I can see CMap is actually the color. No, this documentation is too simple. They should have more, include more details. CM, we apply something called cool warm. Cool warm is actually the higher value will be like red, and the lower value will be blue. Okay, so then I'm gonna just copy and paste here. And indeed, this is the result that we showed there. And I probably need to change spheres, not sphere. This is a paraboloid surface plot with contours. Okay, so this is the thing for this example. And the next is we're going to see how to make the 3D subplots. So we have made the 2D subplots. Unfortunately, Matplotlib make the 2D and the 3D subplots, using different syntax. Here for the 3D subplots, since when some of you may have already observed that when we add a 3D or when we make a 3D plot, it uses add a subplot. And it's correct that for 3D, no matter how many plots you have, even if you have only one, so in 2D, it's just PLT the plot. But here, even if you have only one, it will consider it as one subplot. So it actually makes it easier for us to create subplots because we just need to write down the coordinate. For example, this is one, this is, let me see, this is one, and then this is 2, this is 3. This actually makes our things easier. Okay, so now let's see here. We have the sphere. Let me let me be lazier. I will copy and paste now. Let me copy and paste from here so that I'll where is the okay, but I will still need to make it consistent. I will have these. Actually, I don't need the CM anymore. Okay, so now I first of all generate a pi, generate a theta, generate a phi, and now I have the x coordinates. Okay, so now I will create the what? Uh, add the zeros subplot. So I can say dot add subplot here. I directly have 2, 2, 1. Projection equals to 3D. So here, let me put together x, y, z, and then I'll have x dot that. That's that. Okay, so it's gonna be the scatter sphere scatter plot. And dot scatter, not dot plot scatter. Okay, here we go. And in my slides, the second one is what the first one is scatter. The second one is surface, and the third one is contour. Okay, so I can just copy and paste all these. One plot, and then x is 2, 2, 2, no longer 2, 2, 1. And then here I'm gonna replace the scatter by the plot surface. Regret to remove the previous one. Surface XYZ, and then I can change surface plot. Okay. So here, if you run it, it will create something interesting. See, did you realize something's wrong? That I expect that I should have two things, two subplots, but it shows only one subplot. The reason is because that's again the matplot library things. The reason is because here, if I write it this way, it doesn't understand that it would be the first, it will be everything like in one plot. Indeed, you see, it gives you two plots in which the first plot, you know, only shows the second subplot, and the second plot only shows the first subplot. To disable this, what you can do is here to force Python to create a figure. You can say fig equal to plt dot figure. So if you're writing this way, this fig become a fixed object. The difference here is that Python understands it as plt.figure. Here you create a figure and you add you add a subplot in this position. And now when you do this one, it creates another figure and you add a subfigure here. And that's why it causes the error. However, if you write fig equal to this, so fig is now a fixed uh, object. And then you make it in this way, so it won't create new figures anymore, and hence it will be all together. Okay, now let me add the last one. 1, 0 subplot at 2, 2, 3. And then the third one, I use a contour 3D. Contour 3D, XYZ. And now I can just make contour product. Okay, we're done here. So this shows how to make the 3D subplots. Finally, as an example of all these 3D plots, we still use the linear regression. And I have the data here, which is 3D linear regression. Let me open my data. Okay, so here you can see it's a 3D composed of 1D, one dimension for the response, and the two dimensions, x1 and x2 for the attributes or for the features. Okay, so now I have where this now I have this. So remember before remember before we've already created a class, so we can just copy it back. Here we go. Oh, we're here. we can just copy and paste this class. And then we need to rewrite that plot function, however, which exercise? Exercise 4.4. Okay, so I have, oh, okay. So I copy and paste all these. Let's see what we need to change. So first of all these initialization functions, nothing need to be changed because it's just gather data, computing, split the data, and then fit the model and then make the predictions. What we need to do is here we will not make a subplots. Let me see, what did I do here? We will not make a subplot anymore. Instead, we just make one plot. The difference is that here we have the 3D instead of 2D, and hence our predicted function becomes plane instead of a line, as what we showed, in exercise 4.4. And sorry, I realized something's wrong here. It should be 4.4 instead of 5.4. So I forgot to change it. It should be 4.4. So now let's see how can we modify this thing. So I will make it to be plot 3D self. First of all, here this one will be changed. Plot 3D. Okay. So now first of all, I need to add. I can just delete everything, I guess, just in case I make any of those kind of mistakes. I'll have x equal to plt dot figure dot add a subplot projection equal to 3D. Okay, so now I first need to what? I first need to plot all the, let me see. Okay, I first need to plot all the training data, then the test data, and then the play. Okay, so now let me plot the training data. Plot the training data set. Okay, I can have x dot plot and then self dot x train self dot. Oh, wait a minute. Well, it may be wrong because it's a 2D. It's not a what? And then let's say label. Let me just run it. I'm curious to see what's gonna happen. It should be something wrong here. The data's not. Oh, self dot data. What? Where? Line 10. Okay. So okay, let me see. It should show you something wrong because of plot. Something in the plot function is wrong. Let me see here. Yes, here we go. So one important thing, as what we wrote in the previous example, the same thing. Here, when you make it, you have to say self.xtrain column 0. Why? Because don't forget here, our projection is 3D. So we will need to have x, y, and z. Z is clearly self.y train. But for your x and y's, remember, it's it's here. It's gonna be the first column and the second column. And hence, here, when you're writing this way, x train, okay. And then I will have the column of the x train. I will have, you can either have it to be x1, x2. Here we go. Or you can have something as what I wrote in the slides, which is to cite the column self.xtrain column 0, self.xtrain column 1. Both works. Okay, so now I'm gonna print the what? I'm gonna plot the test data set, and it's pretty similar. You just exchange, replace train by test. Okay, finally, I'm gonna plot the what? I'm gonna plot, let me use, I used what? I used the Y, okay, Y triangle. Finally, I'm gonna plot that plane. So if I run it now, you will see why? Let me see here. Oh, self. Well, oh, okay, here, Y test, my Y train. Okay, so these are my training and the test data. Now I want to plot a plane. Remember, how did we do here in this, where it is, in this example? How do we plot this one? Similar things, right? We generate, use MP, the linear space, generate an X, and calculate the corresponding Y, and I plot it. Okay, similar things. I'm gonna generate XY coordinate using the what? Using the mesh grid, plot the predicted plane. And then I'm gonna what? Then I'm gonna make the uh uh compute the z. And so I will first have, let's say, x equal to, I better not use, I may use ABC. Yes, I'm using ABZ here. Let me use, follow my slides. A equal to MP dot linear space. To get a linear space, I want to get the, the x, what, the self dot x dot mean, and be careful that it's not only mean but zero. Why? Because I have two x's. I have x1 and I can delete this. I have x1 and x2. I have two coordinates here. So you do need to add this one mean, and then I will have self dot x dot max 0. So this is to generate the x, like the linear space in the range of x1, and then copy and paste. It's gonna be, you just, this is for x2. Oh, and now I can have what AB equal to MP dot mesh grade AB. Okay, now I can just make it to be Z. Remember, Z should equal to what? Z should equal to dot intercept plus, and then I will have the beta one, which is self dot model dot coefficient. Oh, this one 0 times A, which are generated here, plus this times B. Okay, so now I can just plot, use a surface plot, dot plot surface, and then I can have A, B, Z, and then I can say color equal to red probably. Yes, color equal to red, and then alpha equal to, let's say, 0.5, and label. Anyway, let me just start to make it to see whether everything works. And now let me just create, and let me see. Make my life easier, I'd better set up this. Okay, here we go. So indeed, you can see this one is the plot plane, and the 2 points. There are two data sets. These blue ones are the training data set, and these yellow triangles are the test data set. And indeed, you can see the result is, let me see the coefficient. It's 0.87, the R square score. It's actually a pretty good fit. Okay, so this is, I believe this is the end of, yeah, this is the result. So this is the end of this lecture, which basically shows how to use those basic functions to make the 2D and the 3D plots and or subplots in by Matplotlib. Okay, after finishing this, we can actually start with the, let me start, I know it's almost the end. Let me start very little of this part, which is lecture 5. Lecture 5 has been uploaded. upload it, but I realized that I still need to add something, which is about the applications by Python. So we've already introduced linear regression one, which is in lecture 3 here. And by linear regression one, we mentioned the basic points of this. But here we will first introduce the concept of overfitting, and then we will have a review of the linear regression. Uh, Overfitting actually is something, when a model is excessively trained on a specific data set. So be careful here, the point is on a specific data set. That means, the overfitted model performs almost perfectly on this specific training data, but fails to generalize well enough to new unseen data. Pay attention. Why do we need to generate those kind of data? The meaning for us to generate. Sorry. Why do we need to make a fit, or have those kind of regression models? The meaning is I want to predict future data. However, if your prediction works only well in this training data. So what's the point? I cannot predict my future data as well. And hence overfitting is actually a very dangerous thing. So let's consider, using the same training data to generate to fit to get these three fits. In case A, looks like we have a perfect like fit. Why perfect? Because you can see every point lies accurately on this line. But these, and hence, let's say the RSS sum of a square residual is 0, looks perfect, right? However, don't forget that here we are actually fitting 8 data points using a 7th degree polynomial. So in other words, we have 7 data, and we have 8 data, and we have 8 variables to be fit as well, which are beta 0 to beta 7. So of course you can get an accurate, a perfect fitting, but this is clearly overfitting. It works well in this data point. However, what if my next data point is, if my next data point is here? By comparison, you can see the result of the line, the result of our fitting. It's gonna be, a function something like b up. So it's clearly a very bad prediction, and hence this is overfitting. In case B, we have what? In this case, we don't have overfitting anymore because these points are very far. In this case, we will have a very large RSS. Remember, the RSS is just a summation of, you know, the residual sum of squares. It is the summation of the squares, sum of the squares of the distance here. And you can see here, oh, sorry. And you can see here, these distances are very, very far actually. So it's clearly not an overfitting, and it's the opposite, which is called inaccurate, which is called inadequate model, and this is also not a good fitting. A good fitting is in case number C, which is, well, it's a kind of like normal, or I can say a balanced RSS. And also the RSS is not too small, like 0, something like that. Also not too big, which is a underfitting. It's something between them, and hence it's a good model. So here, it's a review of the linear regression. Recall that in linear regression, given those points, we first define a function f to be this way, and then I'm gonna define, I want to find out these beta parameters such that, the whole RSS is minimized, and using the normal equations we have already seen in lecture 3 that the solution can be given by this one, which is known as the OLS, ordinary least square estimator. And the n is the number of observed data points, and the p is the number of attributes or features for each data point. And let me see here. We define beta, the dimension of the beta is rp plus 1, and the dimension of data matrix X is n by p plus 1. Why p plus 1? Because the first column is always 1, which is, let me see, where it's like this way, n by p plus 1. Okay, Now let's see. We actually have two problems in the traditional LSLR, least square linear regression. The first problem is what if n is less than p plus 1, or even n is less than or less than p. So recall n is the number of observations. In other words, we'll have some data points which is in this shape, which is like this way, you know, because the traditional case is, let's say, oops, let me erase everything. Because traditional case, it's in this way. We can see it's a rectangular, but it's a rectangular very, very long and not very wide, meaning that we have very small number of parameters or attributes. And by comparison, our number of observed data is way, way, way bigger. But what if the structure is the opposite, which is, for example, if I have, let's say, 1,000 attributes, while I only have, let's say, 33 observations. In other words, I have 1,000 features, but my observed data or my total data is only 34. Then what's gonna happen? What's gonna happen is because in the normal OLS estimator, we have the inverse of XTX. However, if your n is less than p, mathematically we can prove that this XTX is not of full rank. Once this XTX is not of full rank, then the inverse of matrix does not exist. And hence, this OL solution is invalid. Then this is a big issue. And people may ask, hey, is it? It's an issue, but in practice, is this case, which is, let's say, I have many, many features, and I have only very, very limited number of observed data. Is this practical? Actually, yes, it is practical. A very, very typical example is in those biomedical science or those kind of pharmaceutical research. In this kind of research, data collection is very very costly. Why? Because you will need a lot of those kind of pressure metals like a gold, silver, those kind of things. And to get one group, one data point, it can cost you a lot of money. And hence, given limited budget, you don't have enough money to generate a lot of uh, a large number of, let's say, observations. However, the number of attributes to be considered can be very, very large. Why? Because consider you have, let's say, Q fundamental attributes. Q can be those kind of different chemicals, you have those fundamental things, and then you may have 2 to the power of 2 number of parameters. Why? Because for each parameter, for each those attribute, it will be whether a specific attribute, a specific chemical is needed. What I mean is, for example, suppose I have, let's say, like chemical 1, chemical 2, and the chemical 3. So our first attribute will be, for example, 000, meaning that I don't have any of those 3 chemicals. And my second one can be something like 001, meaning that, okay, I don't this data point that doesn't have chemical 1 and chemical 2, but this data point that does include chemical 3. And in like this way, you totally can have what? Oh, it's not smart enough. You totally can have from 000 to 111, right? And hence it's 2 to the power of 3 equals to 8. 8 parameters, 8 attributes you need to consider. Well, as you probably know, if I have, let's say, if I have 10 chemicals, then 2 to the power of 10 is going to be what? It's going to be 1024. And then I will have 1024 such attributes. By comparison, I may not have enough money, enough budget to conduct this, to get these 1024 observations. And hence, in this case, I will have n, the number of observed data, as less than or equal to p plus 1, where p is the total number of attributes. We can, in some extreme cases, we can even have n as less than p. Then we'll have the trouble. Why? Because the inverse of XTX does not exist, and hence this LLS solution is invalid. Um, In some cases, you can also solve it. A typical example is I can, instead of using the inverse, the exact inverse, I can use a pseudo inverse, which is NP pseudo inverse. I'm not sure whether I've heard of it. If you are interested in how to get it, you can just search this one. You have a Google search, and then it will, I believe there's a Wikipedia page about what is the Moore Penrose inverse. Basically, it's just a graduate like calculation method to use Hermitian, and hence it can guarantee that the pseudo inverse is always exist, and then we can calculate a pseudo like OLS estimator. This is method number one. Method number two is to use the regularization method, which is actually the main topic of this lecture. Uh, so this is the first shortcoming. The second shortcoming in traditional LSLR is that what if some beta elements, are extremely big or small, compared with other beta points. So for example, I believe here I have two examples here. The first example is if your beta equals to 5.5, 100, negative 0.1221. Clearly, this beta 2 equal, I define this one to be beta 0. So this beta 2 equals to negative 0.1 is tiny compared with all other, those numbers. So a natural question is, since this one is so small, is there a way I can just ignore it? By ignore it, I mean to drop this parameter and set the corresponding beta 0 to be 0. Unfortunately, in the traditional LSLR setting, all these parameters must be considered, and hence the answer is no. You cannot do it in this way. However, later we can see by some tricks, by some techniques, we can do something actually pretty similar. On the other hand, is a very large case, which is you see here, if my beta 0 is still 5.5, beta 1 is 100, beta 2 is 2 to 1. But my beta 2 this time, my beta 3 is 2 to 1, sorry, but my beta 2 this time becomes 1 million. And hence you can see this beta 2 equals to 1 million actually dominates the entire beta because compared with 1 million, all the other three numbers are super small. So is there a way I can just make it to be, for example, 0, 0, 1 million, 0, make it in this way? And again, the answer is going to be no. Why? Because in the traditional LSLR, all the parameters you must be considered. And hence, these two methods do not directly apply. However, later we will see by applying some tricks, you can actually, apply this methodology. One thing I do want to mention here is that in general, the more parameters a model has, the more complex the model becomes. So whenever possible, we prefer a simpler model, a smaller model with fewer parameters for better interpretation, interpretability, and efficiency. And later we will see how to use regularization to amplify this, to implement this idea. Okay, due to the time limit, I will finish my lecture today. Thank you so much, and see you on Thursday.